Good afternoon, I'm Giacomo Mazzola from the University of Bologna, and this is a brief summary of the mechanical properties and the microstructure of three different high-performance nickel-free powder: the Astalloy 85MO, the CRA, Astalloy CRA with 0.25 of carbon, and the CRA with 0.6 of carbon. In particular, the presentation is focused on the goals of the experimental activities, on the material and methods used for the activities, and finally on the mechanical and the microstructural characterization results. So the two main goals of the experimental activities are the first one, the microstructural and mechanical characterization of three different nickel-free powder subjected to different parameters of sintering and thermochemical treatment. And then we have the data analysis of the result and the comparison of the performances of these three nickel-free powder with the data of other powder containing nickel and forged steel. The tested powders are three pre-alloyed iron powders of the Astalloy family. The first one, the 85MO, is alloyed with molybdenum and 0.25 of carbon. And the other two powders are CRA powders alloyed with chromium. And the first one has 0.25 of carbon, while the last one 0.6 of carbon. All the powders were mixed with the solid lubricant, and then they were compacted, sintered, and the first two powders were carburized and heat treated, while the last one was just induction hardened. Moving to the experimental activities, the first analysis was the density measurement, and the density results are similar for all the three powders and in line with the expected density recommended by Hoganas. And we can say that the process parameter used for these three powders are effective, looking at the density measurement. Yes, after carburizing, quench and tempering, we performed the hardness profile to evaluate the case depth of the three powder. In this image, we can see that the Astalloy CRA in blue color show a case depth about 0.7 millimeters, while the 85MO and the CRA with 0.6 of carbon show a case depth respectively of 1.6 and 2.7 millimeter. And looking at the case depth of the last powder, we can say that all the section of the tensile and the fatigue sample is hardened. The microstructural analysis confirmed the profile hardness. In fact, looking at the Astalloy 85MO, we have a martensitic binitic structure at the center, while due to the different content of carbon and the different cooling rate, the microstructure are 100% martensitic at the surface. For the same reason, the microstructure of the Astalloy CRA with 0.25 of carbon are a mixture of perlite, bainite, ferrite, and some martensite at the core of the samples, while the martensitic of the same sample is completely martensitic near the surface due to the cooling rate and the carbon content. And finally, the microstructure of the astalloy shear A with 0.6 of carbon is martensitic kinetic at the center of the samples, while it is martensitic on the surface due to the different cooling rate between the center and the surface. Moving to the mechanical characterization and in particular to the tensile test, the 85 MO show the best behavior in terms of tensile strength. And then we have the CRA with 0.25 of carbon with a medium tensile strength, but with a high standard deviation of the result. And finally, we have the CRA 0.6 of carbon. If we compare the result of the 85 MO with other two powder containing nickel, we see that the results are similar, while if we compare the same powder, the 85 MO, with the result of a fourth steel, we are about 200 megapascal lower due to the different production process. We have also carried out the bending test, which is the most common and the quick test to evaluate the strength of a sintered part. And also in this case, we see that the strength of the result is the same as the result of the tensile strength. In order to evaluate, in order to explain the mechanical behavior of the powder and the deviation, the height deviation of the shear A tensile result, we analyze the fractal surface of the sample. For the astalloy 85 MO, all the samples show a lot of pores, which are characteristic of these materials, and they are the reason of the very low elongation of the sample during the tensile test. And then we have ductile areas with dimples and brittle zone with cleavage fracture mode. The high standard deviation of the shear A can be explained comparing two different samples. The first one, in green color, is a sample with a high tensile strength, while the second one, in the red color, is a sample with a low tensile strength. The first one has pores, dimples, and cleavage area as the samples made by 85 MO, while the second one, the red one, has a low area with dimples and a lot of flat area, which means that the fracture moves along the green boundaries and it leads to a very low tensile strength. And finally, we have the surface of the samples made by astalloy shear A 0.6 of carbon. In this case, we have, of course, pores, some dimples, and a lot of brittle area. The last test we performed is the fatigue rotating bending test, and also in this case, the result, the trend of the result is the same. The 85 MO show the best behavior in terms of fatigue strength, and then we have the shear A with 0.25 of carbon, and finally the shear A with 0.6 of carbon. We can also notice two other important things. Despite the high standard deviation of the tensile result of the shear A 0.25, the fatigue result are characterized by a low standard deviation. And the second one is that the the ratio between the tensile and fatigue strength of these two first powders are about 50%, while the last powder show the same ratio, about 33%. And once more, the fractal surface can explain the reason of this different ratio. In fact, despite the different chemical composition and heat treatment parameters, the nucleation of the fractals start always near the surface from the pores. But in the propagation area, the two powders with a ratio about 50%, we have striation and, of course, pores. While in the last powder with the ratio about 33%, we have striation and a lot of brittle areas with the cleavage. The final fractal surface are similar to the surfaces observed for the tensile samples. Concluding, we can say that the Astalloy 85MO has performances comparable to other nickel-containing powders, and we think that these properties could be further increased by optimizing the carburizing treatment. The second powder, the CRA 0.25, is likely less performing than the 85MO, but optimizing the sintering process and the heat treatment, it could reach performance in line with the previous powders. And finally, the Astalloy CRA with 0.6 of carbon has shown mechanical properties that don't allow its use for the production of high mechanical components. Thanks, and if you have any question, I'm happy to answer.